This lecture is part of an online course of multivariable calculus, and I'm going to talk about the second derivative test to classify critical points, whether they are a local mean, local max, or neither. So let me start by reviewing the single variable case. If we have a function of single variable like this, suppose derivative at the point A is equal to 0. Then we take the second derivative at the point, and if the second derivative at the point A is positive, then the point A is a local mean, like this. If the second derivative at the point A is negative, then the point A is local max. We have like this graph at the point A. If the second derivative at the point A is 0 or undefined, means that the second derivative does not exist, then this test is not conclusive. So we cannot conclude that if it is a local mean, or it could be local max, or it's neither. How about the two variable case? If we have a function of two variables like this, f of x and y equals to z, then we say that let the point A and B be a critical point of the function f. On the critical points, we might get the gradient of f at a point is equal to 0, which means that the partial derivative with respect to x at the point and partial derivative with respect to y at the point at the same time they are equal to 0, or fx at the point, or fy, the partial derivative with respect to y at a point does not exist. If we have this situation that both of them at the same time are equal to 0, or if just either of them, at least one of them, does not exist, then we have a critical point. So if we have a critical point at the point A and B, then let the second partial derivative with respect to x, the second partial derivative with respect to y, and the second partial derivative with respect to x and y are defined and continuous in a neighborhood of A and B. So we need to have these two conditions. First, the point is critical point. The second one is that the second partial derivatives are defined and continuous. Then we're going to compute d at A and B. What is d? d is the determinant of f of xx at a point AB, f of xy at the point AB, and then f of yx, f of yy. So basically it's a matrix 2 by 2, fxx, fxy at the first row, fyx, fyy at the second row, all of them at the critical point, and we are taking the determinant and we call it d. So d is just basically fxx, fyy. So I'm just calculating the determinant, which would be this times that minus this times this. So fxx, fyy, and then fyx square. So fxy and fyx, that are equal to each other because they are defined and continuous. Okay, and we are calculating this value at the critical point. Now the situations are like this. If d is positive and fxx at the point A and B is positive, then we have a local mean. So the point A and B is local mean. So if we have these two situations together, okay, now if D is positive and f of xx at the point A and B is negative, then we have a local max at the point A and B. So AB is a local mean, or AB is a local max. And if D is equal to 0, if D is negative, this is one of the cases, if D is negative, then the point A and B is saddle point. And if D is equal to 0, we cannot conclude anything from this test. Okay, so if we have a local mean, we might get something like this at the point A and B. If we have a local max, we might get something like this. And if we have a saddle point, we might get a saddle like this. Okay, so let's look at one easy example to just see how to apply this test. The example is this: find and classify critical points of these three functions. I'm going to start with the first one. So to find the critical points, I need to find the first derivative with respect to x, and I'm going to set it equals to 0, this first derivative with respect to y, and at the same time I'm going to set equals to 0, and then you see that I got the point 0, 0, so it's the critical point. I'm going to calculate D. For that, I need fxx, which would be 2, fxy, which would be 0, fyx, which would be 0, and fyy, which would be 2. So D would be 2, 0, 0, 2, which is 4. D is positive, and fxx at the point 0, 0 is 2, which is positive. And as you see, it doesn't matter because they are constant. It doesn't matter that if I put the point 0, 0 into there or not. So D is positive. Partial derivative with respect to x is positive, the second partial derivative with respect to x. That's why the point 0, 0 is local mean. So we might get like that. Okay, let's look at the graph of it. This is the graph of x squared plus y squared, and it's the paraboloid like this. Very good. Look at the second one. I have g of x equals to negative x squared minus y squared. So I'm gonna set gx negative 2x, gy is negative 2y. I'm gonna set both of them equal to 0, and then 0, 0 is the only point that satisfies both equations at the same time. G of xx is negative 2, g of xy is equal to 0, g of yx is 0, g of yy is negative 2. So let's calculate D. I get negative 2, 0, 0, and then negative 2. I get 4 again, which is positive, and fxx, g, actually the function is g. gxx is equal to negative 2, which is negative. That's why the critical point is local max. So we might get something like this. Okay, let's look at the graph. This is the graph at the point 0, 0. You see that we have a local max. Okay, this is the function negative x squared minus y squared. It's like this. Okay, very good. Look at the last one. For the last one, I have h. So hx is 2x, hy is negative 2y. Then at the same time, I get 0, 0, hxx 2, hxy 0, hyx 0, hyy is negative 2. Let's calculate d. So d would be 2, 0, 0, negative 2, which is negative 4, and it's negative. When we get a negative as d, then the point is saddle point. Okay, so the graph of a saddle point is something like a saddle, like this, for example. Let's look at the graph. There you go. This is the shape of this graph, and as you see at the point 0, 0, in one direction it goes up, and in the other direction is like the upside down parabola. Okay, so we get a saddle point at the point 0, 0. So this is how we use the second derivative test in a very simple example like this.